Hello students, in this video we are going to discuss the magnetic field due to a current carrying element, that is nothing but Biot-Savart's law. In the previous case we have discussed the motion of a charged particle within magnetic field. Here if you are taking any current carrying conductor, how this current carrying conductor will produce the magnetic field, and what is the value of magnetic field, on which factors the magnetic field depends. So this information is given by the Biot-Savart's law. So we are going to discuss in detail here. It is one of the important concept. Please listen carefully. Assume that it is a conductor. It is a conductor XY through which the current I is passing. Due to this conductor, we need to find out the strength of the magnetic field at certain distance r. Before that, we will take a smaller element. A smaller element is suppose say dl. While we are writing vector form, dl bar. And if you multiply this one with current I dl. So this I dl bar is called as current element. It is called as current element. So due to this current element, at certain distance or at certain position, suppose say point P, we have to find out the strength of the magnetic field, suppose say dB, that is a dB bar. But you are aware of right hand thumb rule. From the right hand thumb rule, we can decide the direction of the magnetic field. dB is here, it is into the plane. Assume that this wire is in XY plane, that is on the monitor. The dB will be into the monitor or into the board. So we can decide this one with the help of right hand thumb rule. And the angle between this current element and this position vector, suppose say r bar, is theta. Now according to Biot-Savart's law, the magnitude of the magnetic field, I am taking just to dB, is directly proportional to the current I, and it is also directly proportional to dl and inversely proportional to the square of the distance. And what is its direction? The direction will be perpendicular to the plane. The direction of the magnetic field is perpendicular to the plane containing dl bar and r bar. So therefore finally we can write vector form. So dB bar is proportional to I dl bar cross r bar divided by r cube. This one also we can write dB bar is equal to mu naught by 4 pi. If you remove the proportional, you can take a proportionality constant. Its value is mu naught by 4 pi I dl bar cross r bar divided by r cube. It is a vector form of the magnetic field. And where mu naught by 4 pi is a constant and its value is mu naught by 4 pi value is 10 power minus 7 Tesla meter per ampere in SI system, and this mu naught divided by 4 pi value will be equal to 1 in CDS system. Right. The direction of this dB will be perpendicular to the plane which contains dl and r here. Now we will see few points based on this one. The similarities and the differences between the Biot-Savart's law and Coulomb's law. Both are long range. Biot-Savart's law and Coulomb's law. In Biot-Savart's law, we are finding the value of dB. In Coulomb's law, we are finding the force or electric field. In both cases, both fields are depend inversely on the square of the distance from the source to the point of interest. So both are long range. And the principle of superposition is valid or applicable to both the fields. That is magnetic field as well as electric field. The magnetic field is linear inside the source. That means dB is directly proportional to IDL, just as the electrostatic field is linear inside the source. And electric field is produced by scalar source, namely electric charge, but magnetic field is produced by a vector source, that is IDL bar. And the E bar is along the position vector. Electric field is along the line joining the source and the field point, but the magnetic field is perpendicular to the plane contain position vector and the current element. There is an angle dependence in the Biot-Savart's law, but it is not within Coulomb's law. And one more important point, magnetic field at the point in the direction of dl is 0. Here we have taken like this. If you take along this point, the magnetic field will be 0. The point in the direction of dl, dB value will be 0 here. So this is Biot-Savart's law. Now coming to one of its application, that is magnetic field on the axis of a circular current loop. And this current carrying loop is also acts as like a magnetic dipole. Okay, we'll see here. Assume that we are taking a current carrying loop. This current carrying loop is in the plane of YZ. Is in the plane of YZ. And this is x-axis. This is the axis of the circular loop also. Assume that the current is I passing through the loop. Here one important point is we are taking the two elements dl here. Here one dl I am taking IDL through which the current is coming out. Here one more element, there is IDL bar, in which the current is entering. Now because of the current carrying element IDL on the top, so we are going to find out the magnetic field at point P on its axis. It is at distance, suppose say R. IDL is a distance R from the point P, and the radius of the current carrying loop is capital R, and from the center the point P is a distance x. Now what will happen? According to Biot-Savart's law, the magnetic field due to this IDL will be like this. Suppose say it is a dB. This dB should be perpendicular to this R and perpendicular to IDL. Now we are resolving this dB into two components. One is dB perpendicular, I am writing it is along y axis, and dB parallel or dBx along x axis, and dB is making an angle theta with x axis. Now we will apply the formula dB bar is equal to mu naught by 4 pi into IDL bar cross R bar divided by R cube from the Biot-Savart's law. And we can write DL bar cross R bar magnitude as simply R into DL, and the above formula just magnitude alone if you are writing dB is equal to mu naught divided by 4 pi into IDL divided by R square, and that is also nothing but mu naught divided by 4 pi into IDL divided by R value. So this one will be look like a right angle triangle. The relation between small r, capital R and x is small r square is equal to capital R square plus x square. Take it is equation number 2. Now, if you are resolving dB, this dB is because of IDL which is at top. dB perpendicular dBx. Suppose if you are taking IDL bar at the bottom, because of this one downwards also dB will be there. If you are resolving into two components, dB perpendicular and dBx, dB perpendicular will be get cancelled. So the vertical components won't exist. Only net field will be along the x component. So therefore here we will take only dBx alone will exist. So due to complete circular loop, we can take integral of dBx is equal to mu naught divided by 4 pi integral of IDL divided by R square plus x square into cos theta. This one will be because dBx is equal to dB cos theta by resolving, and dB perpendicular is nothing but dB sin theta. This cos theta I am writing here, that is equal to mu naught divided by 4 pi. This dBx is nothing but we can take simply B, the total magnetic field due to the current carrying loop at distance x from its center on its axis, into I by R square plus x square into cos theta. Cos theta value can be, it is theta, then automatically this one will be 90 minus theta. We can write cos theta value will be R by x square plus R square whole power half. Will get it. It is cos theta value into DL integral of, where cos theta is equal to R by x square plus R square whole power half. So from this, after simplification, mu naught I R divided by 4 pi into R square plus x square whole power 3 by 2 into integral of DL is nothing but we have 2 pi R. Why means we are taking a smaller element DL and we are applying it for complete loop. The circumference of the loop is nothing but 2 pi R, and 2 pi will be get cancelled. We can get the same is nothing but mu naught I R square divided by 2 into R square plus x square whole power 3 by 2. This is the magnetic field due to the current carrying loop. In vector form we are writing, it means B bar is equal to mu naught I r square divided by 2 into r square plus x square whole power 3 by 2. It is along x axis, that's why I cap we can use here. Suppose say at the center, at the center of the loop, raise x is equal to 0, then this value b naught is equal to, we can write mu naught I divided by 2r. This is the magnetic field at the center of the loop. And suppose say if we are taking the loop is like this, and the current is passing like this, then with the help of right hand thumb rule we can draw the magnetic field lines like this. Such a way that these arrow marks are upwards. So this direction of the magnetic field is decided, can be understood with the help of right hand thumb rule. And one more important point here, case 2, instead of complete loop, if we are taking an arc, this is some arc through which current I is passing, at its center the magnetic field due to this current carrying conductor bent in the form of an arc. So there is a B at the center of a current carrying conductor bent in the form of an arc of radius r, subtending angle theta at its center, can be taken as, just I will take the magnitude alone. B is equal to mu naught I divided by 4 pi r into theta. Suppose when theta is equal to 2 pi, that means for complete loop, that is for complete circular loop, so this formula can be B is equal to mu naught I divided by 2r only. Suppose if you are taking when theta is equal to just pi, B is equal to mu naught I divided by 2r. So that is field at the center of a semicircle. That means if we are taking, this is a semicircle of radius r, then the magnetic field at its center will be mu naught I by, sorry, it is mu naught I divided by 4r, mu naught I divided by 4r. So this is one of the application of Biot-Savart's law, that is magnetic field due to current carrying circular loop. Thank you. I hope this concept is clear. It will be important for your examination, for the board examination.